Hello everyone. Uh, Welcome to the mind map series, and we are going to discuss the chapter of current electricity in this one. So, first of all, in the previous mind map, I think we have already discussed about electrostatics, so some of it will be used here. For example, we will start with the electrostatics itself. What was electrostatics? It was the static charges. But in the current electricity, we are talking about dynamic charges, a motion of charges, and the result of that motion. First of all, let's take an example. This is a current wire in which if a current is flowing, let's say whatever you understand by the term current that is flowing, basically it should mean that some charges are moving. This is negative and this is positive. So some protons may be moving or electrons may be moving, but protons are too heavy to move. That's why electrons are the ones that carry the current, and they will be going in this direction. Now, do you think these electrons will just go ahead? For example, this is an electron, and this some E is the electric field that is applied here. So, do you think the E field is getting applied in this direction, due to which the electron will experience a force in this direction, and what that force is going to be? F is going to be the charge on one electron E and capital E. This is going to be the force, due to which it will accelerate, of course. So I can write mass into acceleration is equal to the force, that is equal to E into capital E. Small e is the charge on electron, capital E is the electric field intensity. So acceleration from here you got by m. So what we got from here is there is some particular acceleration that it will have, that the electron will have, and is this going to be a constant acceleration as per uh, our derivation, small derivation, if I can say so? As per that, it is going to have a constant acceleration. But shouldn't that mean that if it has accelerated from here, the velocity will continue to increase? So isn't it perpetual increase in velocity? Of course, but that is now how it happens. Otherwise, um, we'll encounter a failed circuit, right? Some portions may be more heated, some portions may be less heated. That may be the case, but वैसा कुछ होता नहीं है, क्योंकि इलेक्ट्रॉन्स एक कांस्टेंट वेलोसिटी से मूव करते हैं. अभी हमारा कुछ समझ में आया तो है नहीं that we have got an acceleration, but constant velocity भी बोल रखा है. So how that happens? It is actually not a free motion, but multiple obstructions are there. For example, the race that Usain Bolt ran was this race having no obstruction, and this is called some sort of if you know, steeplechase, in which you have obstructions and you have to jump over them. But in this motion of charges, there are heavy atoms in between them, and जब भी उनसे टकराता है कोई इलेक्ट्रॉन, so they momentarily come to rest almost. Let's say this is a big atom and another electron comes and it collides. After that collision, it may move here, but the velocity is lost, right? So basically, if I start from here, my motion, the electron's motion will look something like this: going straight, collision, going straight, collision, going straight, collision, going straight, collision. So it will be something like uh, an obstructed motion again and again, but after every obstruction, the electron experiences a force again, this one, due to which it accelerates again, and it accelerates to gain a velocity until it collides with next atom. So its life is like that only, that एक बार वो शुरू कर दिया, वो टकराते रहेगा, रुकते रहेगा, फिर भी चलते रहेगा. सी हाउ determined the electron is. So that is the general motion of the electron. But what we are going to discuss here is, on average, what is the time it takes? What is the time it takes between two collisions? That is the time the electron is going to experience a constant acceleration, right? A constant acceleration and hence an increasing velocity. अभी यहाँ पर velocity कितना होगा just after collision? It is going to be zero initial velocity, and just before the collision, let's say the velocity is v, then we can definitely find out v, right? Because we have the time interval between them, which is, I'm calling this as tau. Average free path time, I'm calling this. Means on average how much of time it takes between two collisions, that I'm defined as tau. I can definitely write the laws of universal laws of motion, right? Equations of motion. V is equal to u plus at. So v is equal to what? V. Now here u is equal to 0, so I can put it at 0, and acceleration is this one, small e capital E by m, small e capital E by m into tau. This should be the maximum velocity that electron can achieve after its motion through a time period of tau seconds. So I'm calling this as drift velocity. Why drift velocity? Why not maximum velocity? We are calling this drift velocity because it has been averaged. What we have plugged here is the tau is the average free time, right? So what you'll get from there is the resultant is average of velocities, right? Average of maximum velocities, sorry. So this is called drift velocity because electrons are not going in a straight line, they are drifting in during their motion. That is why this motion is called drifting, and the velocity that we associated with it is called drift velocity. So I hope this was clear. This is exactly what I'm talking about, drift. Let's calculate drift velocity in terms of current. Let's say this is a conductor in which particles are there which can conduct electricity. For example, in case of normal metals, maybe these are electrons. So if I consider this as a cross section, and during a delta time t, this portion, the whatever electrons were there, they have crossed this much length, L length, in delta time t, or delta L length in delta time t, and they have reached here. All right, and I have given this as n is not the number of electrons, it is the number of electrons per unit volume. So if I do that, what I will have here is delta L is equal to yes, I can definitely write it as v drift velocity into delta time t, because v is equal to d by t. So d, which is this much path that electron has covered, should be equal to velocity into time. So that is velocity into time, right? So v drift into delta t, and is equal to, let's write it as such. And what's the amount of charge that has passed through this phase? If I want to calculate the amount of charge which has passed through this phase, it should be the total number of charge lying in this area, right? Total number of charge. So how to find the total number of charge which has passed through this area? That will be the number of electrons that has passed through this area or through this volume multiplied by the charge on each volume on each electron, right? So delta Q is equal to number of electron passed multiplied by charge on single electron, and number of electrons passed should be equal to the total volume multiplied by n. Why? Because n is equal to number of electrons per unit volume. अभी n जो है वो number of unit electrons per unit volume है. अभी उसमें मैं वॉल्यूम मल्टीप्लाई कर दूं तो नंबर ऑफ टोटल इलेक्ट्रॉन्स मिल जाएंगे ना, वही मुझे चाहिए नंबर ऑफ टोटल इलेक्ट्रॉन जो इस फेज से अभी भी पास किए. सो दैट विल बी n into what's the volume of this one. If I consider this as cylindrical, that will be area A, cross sectional area A multiplied by the length delta L into E, right? And here you got n into A into delta L. I can substitute from here Vd delta T into E. This is delta Q, the amount of charge which has passed. If I define a term delta Q by delta T, that is electric current. Electric current, first of all, I'm defining a term here, I is equal to delta Q upon delta T, means number of charge passed or amount of charge which has passed through a particular surface area, rate of that passing of charge, amount of charge passed per second. If I define that, this is called electric current. So by delta T, if I do that, I'll have to divide that on the other side as well. Vd delta T into E divided by delta T. Now delta T gets cancelled out and we are left with NVD A E, right? And this should be equal to delta Q by delta T, which is the current, right? So I have a term for the current which should look something like what you wanted from here. Yeah, VD, NEA VD, right? See, what we got from here is I is equal to NA VD, and if you want VD from here, it will be simply I divided by NAE. That is what has been given in the mind map. तो ये हो गया. अभी I have another term from here, that is, this is current, right? Current. I have some other definition as well, which is called current density. First of all, what do you understand by the term density? Density means it has been normalized with some of the parameter, right? For example, if you talk about density, mass density, it is mass per unit volume. If you talk about population density, it is population per unit area. So in a similar manner, this density has been defined with respect to area. It means basically, if there is this surface area through which some current is passing, then in 1 meter square of this area, how much of the current has been passing? That is the definition of current density. So current density J, it is represented by the term J, is equal to the current by volume, current by area. So if I substitute from here, it will simply J is equal to N A VD E divided by the area itself, area gets cancelled out, and J is equal to N VD E. N is the number of electrons per unit volume, Vd is the drift velocity, and E is the charge on a single electron. I believe we have got this term as well. Actually, current density is very similarly in this manner also. Why? Because cos theta term has been introduced if there is a surface area and electrons are not passing perpendicularly through it. they may be passing from in this direction. Then it is slightly modified as per the flux, whatever definition of flux that we have that we had in the previous chapter. We will use a similar definition to define the current density. So I think average collision time. See, average collision time, that is what we had defined earlier, and that is going to be this equation. अभी यहाँ पर अगर इतना कुछ clear है तो again this is another manner to show it. Why? Because I is equal to Q by T, right? So if I do, let's say this is a wire over which there is this current density. From current density, if I want to find out if I want to find out the total amount of charge which has passed or the rate of charge, I should definitely integrate it with respect to or multiply with area, right? That should be equal to current, but it may be non-continuous area, so I can't definitely directly multiply it. I'll have to use JDA integral for individual areas. What are the small currents or current densities which are passing, and that will give you the total current. I believe this is the same thing that is there. It is just ds and I have used dA, but they are both referring to the area only. All right. अभी यहाँ तक क्लियर हो गया है तो हमें समझ में आ गया कि करंट जो है वो बनता कैसे है फर्स्ट ऑफ ऑल, और एट द एंड इलेक्ट्रॉन्स ही वो पार्टिकल्स हैं जो कुछ वेलोसिटी के साथ जा रहे हैं, नॉट इनफिनाइट वेलोसिटी, बिकॉज इनफिनाइट वेलोसिटी क्यों नहीं हो पा रही है? उनके पास कांस्टेंट एक्सेलरेशन है बट बीच बीच में ऑब्स्ट्रक्शन उनको मिल रहे हैं जिसकी वजह से उसको रुकना पड़ रहा है. एंड एवरेज कोलिजन टाइम हमने डिफाइन किया उस हिसाब से. उसके बाद हमने करंट डेंसिटी के ऊपर देखा. दिस इज मोस्टली द इनिशियल पार्ट ऑफ दिस चैप्टर which is rarely used as per my experience, but it is very important to have a clarity over them. अभी हम आगे चलते हैं कि हमने अभी भी देखा था, क्या देखा था? इलेक्ट्रॉन जैसे आगे जा रहा था, इलेक्ट्रॉन जा रहा था आगे, तो it was facing some resistance, right? It was not easily moving. Some atoms were there through which it had to collide and then restart and then collide and restart. So that definitely is something we call as resistance, right? It is resisting this whatever this matter is, or this whatever, maybe even metal or non-metal, it is resisting the motion, right? It is definitely resisting the motion of the electron. So what I was saying is I have to define this resistance in some terms. First of all, this resistance, let's talk about it. Let's take a cylindrical piece of a matter and we have to define resistance. First of all, if electrons are there and if the length is longer, do you think it will have to face more resistance? Of course. Why? Because if the length is longer, अगर लेंथ लंबा है तो आगे जाते जाते उसको और सफ़र करना पड़ेगा, राइट? स्ट्रगल करना पड़ेगा, बीच बीच में रुकना पड़ेगा, फिर आगे बढ़ेगा, फिर रुकेगा, फिर आगे बढ़ेगा. सो लेंथ बढ़ते गया तो रेजिस्टेंस बढ़ते जाएगा, राइट? बेसिकली, सो इट इज डायरेक्टली प्रोपोर्शनल ऑन L. Now what do you think? If I increase the surface area, is the resistance going to decrease or increase for a fixed length? अगर इंक्रीज कर दूं मैं एरिया तो नंबर ऑफ इलेक्ट्रॉन्स जो फ्री हैं ये करंट को कैरी करने के लिए वो तो बढ़ जाएंगे, और अगर वो बढ़ गया तो इट्स लाइक एक लंबा रेस है और उसमें हमने मल्टीपल रेसेस इंक्लूड कर दिए हैं ताकि हमारे जीतने के चांसेस बढ़ जाएं. तो इसके वजह से resistance should be inversely proportional to the area. Now if I combine them, then I'll have R is equal to some constant into L by A. The constant is given as rho, where rho is the property of the matter through which it resists the flow of charges through it. This is called resistivity. This is resistance. All right. Now, if I have material, or maybe we can define it using an experiment. So this experiment is yes, I and V. So let's say there's this uh, material or maybe heater, and there was this scientist called Ohm who conducted the experiment that if I give this particular amount of voltage, what is the current that is going to flow through this particular device. So he drew this graph I versus V, variation of current with respect to voltage. So he found out that it was actually more of a straight line. So what he basically gave from here is Ohm's law, which is I is directly proportional to V, and if I actually give I is equal to V by R or V is equal to IR. This is the expression of Ohm's law. And first of all, this is V versus R relation, right? V versus I. So if I want to find theta or the slope here, tan theta, what should that be? That should be I versus V, because it is starting from 0, and I versus V is equal to 1 by R, right? If I switch them back here, V versus I graph, the tan theta will become R. No problem in that. So this is called Ohm's law, and this is the experiment Ohm did, I versus V or V versus I graph, and he found out a straight line. So basically I is equal to V by R. If I replace R with this term, it will simply be V by rho L and A. This is going to be the current that flows through the this resistor. What we call it is a resistor, because it is resisting some current through it. What is that is trying to pass through it. And what we had applied here was this, right? I'll use another color. Across this we had applied a voltage. So basically we should have a constant source of this voltage, right? It's not like I applied it here and it remained there for maybe 1 second and then vanished. No, we have to give it a constant supply of voltage, which is called a battery or EMF, electromotive force. Electromotive force. Why is it called a force? It is not exactly a force. It's just uh, it has been named very old in the very old days, due to which it was assumed that this battery is trying to push electrons, forcing it physically. That is why they gave the term EMF, electromotive force. But it is not exactly force. It is the tendency of the battery to push movement of charges. It is the one that is uh, introducing the movement of charges, through which the charges move from here to here and through the resistor as well. So this is what we discussed right now. I think yeah, this one. And I think it's a basic definition that if the resistivity is rho, it means basically it is defining that how much the material can resist. It is the chemical property of the matter through which it is resisting the motion of charges. But there could be another property which is telling me that the more it is higher, the more it is easier to conduct charges. So that is called conductivity. Don't you think they are opposite of each other, resistivity and conductivity? Resistivity is basically trying to uh, contain the movement of charges, where conductivity is basically telling that how easily the electrons or any other charges can move through it. So they should be actually indirectly proportional to each other, and they're actually defined in inverse of each other. This is this thing 1 by sigma, where sigma is the conductivity. Yeah, now we have dealt with this part. Now coming to this EMF that we were defining. अभी EMF है क्या? वही इलेक्ट्रोमोटिव फोर्स दैट इज एक्चुअली, वो एक्चुअली वोल्टेज ही है, बट क्योंकि वो अंदर इलेक्ट्रॉन्स को पुश कर रहा है मूव करने के लिए, इस वजह से हम उसे फोर्स का नाम दे देते हैं, या फिर एक्चुअली जिसने नॉमेनक्लेचर किया था बहुत पुराने टाइम में उसने फोर्स का नाम दे दिया, बट इट इज नॉट एक्चुअली फोर्स, इट इज वोल्टेज डिफरेंस, which is described by the term or the sign this one, where the higher one is positive end and a smaller one is the negative end. So current will always flow in this direction. I mean, it's not essential, but if it is the only battery, then current will flow like this. There could be chances that a battery has been placed in this manner, and the current is flowing in the opposite direction. That may be the case when some stronger battery has been placed in the other part of the circuit, which is stronger than this one, and having more influence on the circuit than this one in the opposite orientation. अगर ये हो गया है तो EMF is equal to this one. You don't need to get into it, it's just the potential difference. Whatever laws of potential difference are there in the electrostatics, they could be easily applied to here, but there's no need of that much of detail in this part. Electrostatics you already know. Now it is equal to the potential difference between the terminals when the terminals are not connected externally, right? So it is basically two plates which are at a different potential, and that's the potential difference, which is called the voltage of the battery or electromotive force of the battery. अभी ये अगर क्लियर हो गया है तो हम एक सर्किट बनाते हैं. अभी सर्किट में एक स्ट्रेट लाइन जहां भी होगा, दैट इज अ कनेक्टिंग वायर, एंड यू डू नॉट हैव टू टेक द रेजिस्टेंस ऑफ दैट, बिकॉज resistance of a conductor is assumed to be zero, although it might not be exactly all zero, except for superconductors. Superconductors are material which exhibit zero resistance. For superconductors, I think there are only few known matters which has been shown to conduct or display the character of superconductivity, and even that at very very low temperature. For example, I think mercury, or yeah, I think mercury displays superconductivity at 0 Kelvin, almost 0 Kelvin. So that's a tough one to achieve. Now let's say this is the R, that is the resistance, and E is the electromotive force. Now of course this is going to be the direction of movement of charges, or sorry, direction of movement of current. The current I'm defining as I. Now this is the only circuit. If I have placed a potential difference of this one E here, the same potential difference must be applied there as well, right? Because ये वायर जो है ना, वायर में है जीरो रेजिस्टेंस, तो उसके वजह से कोई भी लॉस नहीं होने वाला है। तो बेसिकली यहाँ पर V लगा दिया और R रेजिस्टेंस है, तो I इज इक्वल टू V/R हम लिख सकते हैं इस सर्किट में, ऑफ कोर्स लिख सकते हैं। नाउ अगर ये हो गया, समझ में आ गया है, तो आई थिंक वी आर रेडी फॉर दिस वन एज वेल। नाउ yes, let's assume, or first of all, there is this battery, right? एंड बैटरी से करंट निकल रहा है और जा रहा है आर में। यहाँ पर इस सर्किट में हमने ये अज्यूम किया है कि बैटरी आर जो रजिस्टर है उसके अलावा कोई भी पार्ट जो है सर्किट का उसमें जीरो रेजिस्टेंस है, बट दैट इज नॉट ऑलवेज पॉसिबल बिकॉज इट्स एन आइडियल एजम्पशन, और आइडियल तो कुछ भी होता नहीं है। तो एक्चुअली जिस इस बैटरी से पास होते हुए करंट भी थोड़ा सा रेजिस्टेंस फेस करता है। सो अगर उस रेजिस्टेंस जो इंटरनल रेजिस्टेंस इस बैटरी का है जो उसके अंदर है उसको मैं डिस्प्ले करना चाहूँ तो मैं लिखूंगा ऐसे, दिस इज द एक्सटर्नल रेजिस्टेंस, this is the battery, and I'll just draw a small r. This means that small r is the internal resistance of the battery, although it has been shown externally. That is because I can't exactly fit a resistor sign in between the two plates, right? So that is the resistance of the battery, and we'll come to that why how to find the actual or the effective potential of this battery. We'll come to that, but for that I think we have to define few laws for that to happen. Yeah, I think we can go ahead with the, or maybe this is one part that I think I missed while explaining everything, that for example अगर ये कंडक्टर है या फिर रेजिस्टर है, कोई सा भी मटेरियल है, अगर उससे इलेक्ट्रिसिटी पास हो रही है तो कोई रेजिस्टेंस वो प्रोवाइड कर रहा होगा, और रेजिस्टेंस किस पे डिपेंड करता है? वो डिपेंड करता है कि उसको बीच में कितना ज़्यादा ऑब्स्ट्रक्शन मिल रहा है, राइट? बट ऑब्स्ट्रक्शंस कुड बी मिनिमाइज्ड अगर ये सारे स्टैटिक हो, बट इन रियल लाइफ वी ऑलरेडी नो दैट at normal temperatures, even at normal temperatures or high temperatures, the particles actually vibrate along their mean position, right? They vibrate, and while they vibrate, they actually have the tendency to, or the tendency of the electron to strike another atom increases, right? Because it is random motion, due to which resistance increases with temperature, because more the temperature, more the vibrations will be there. अगर ये इतना समझ में आ गया है तो रेजिस्टेंस बढ़ेगा ना, तो हम ये एक अजम्पशन है कि रेजिस्टेंस जो है ना लीनियरली इंक्रीज होता है टेम्परेचर के साथ। दिस इज नॉट एग्जैक्टली ऑलवेज ट्रू, बट फॉर अ स्मॉल window interval of the temperature we can assume that ये linearly increase होगा. For example, let's say this is the resistance and this is the temperature. The actual graph might look like something like this, but हम क्या करते हैं कि let's say this portion to this portion, this can be assumed to be a straight line for a small portion in temperature. So within this temperature difference we define this proportionality, और हम इसके बाद अगर ये प्रोपोर्शनल हो गया मतलब कि R इज डायरेक्टली प्रोपोर्शनल टू, और डेल्टा R इज डायरेक्टली प्रोपोर्शनल टू डेल्टा T, चेंज इन टेम्परेचर, then we can quickly go ahead and give this equation, that R is equal to R naught 1 plus alpha T minus T initial, T final minus T initial. मतलब कि linearly increase हो रहा है. I think we have already discussed equations like this, especially in the rigidity chapter. अभी R और R नॉट को मैं रो के टर्म्स में लिख सकता हूँ. What will the R be? Rho L by A is equal to resistance of the initial part. That will be simply another rho naught multiplied by L by A, because L by A is not changing, neither L not A. This is the assumption. TF minus TI. L by A gets cancelled, and rho is equal to rho naught 1 plus alpha TF minus TI. A very similar equation in terms of resistivity, right? So I think this has been the part that has been discussed here. अभी यहाँ पर अगर समझ में आ गया है तो इसके बाद के पार्ट में जाते हैं. हाँ, see, let's say there is this circuit in which there are two resistors. R1 and R2, and this is E. अभी इसमें हम नेट रेजिस्टेंस कैसे फाइंड करेंगे, मतलब कि टोटल रेजिस्टेंस ऑफ द सर्किट. इस बॉक्स के अंदर कितना रेजिस्टेंस है वो हम फाइंड करेंगे इधर इस I से. सी I जो यहाँ पर फ्लो कर रहा है, क्या वो सेम I इधर भी फ्लो करेगा? करेगा क्या? करेगा कि नहीं, उसके लिए हम दो लॉज पहले डिफाइन करते हैं, उसके बाद इस पे वापस आएंगे. Those laws are, let's say, first of all, ये एक पॉइंट है जहां से मे बी 3 या 4 वायर निकल रहे हैं. इधर से करंट आ रहा है I1, इधर से करंट आ रहा है I2, इधर से करंट जा रहा है I3, और इधर से भी करंट I4 जा रहा है. Then isn't it simply dq1 by dt plus, or what are these basically? dq1 by dt, right? dq2 by dt, dq3 by dt and dq4 by dt. मतलब रेट ऑफ चेंज ऑफ चार्ज पर यूनिट टाइम अगर बता रहे हैं, तो अगर एक छोटा सा इंटरवल लें इस बॉक्स को कंसिडर करके, देन जितना चार्ज आया है इस साइड से dq1 dq2, उतना ही चार्ज इधर से लीव करना चाहिए. क्यों? क्योंकि एज पर द कंजर्वेशन ऑफ चार्ज, लॉ ऑफ कंजर्वेशन ऑफ चार्ज, चार्ज कैन नीदर बी क्रिएटेड नॉर बी डिस्ट्रॉयड. तो अगर ऐसा है तो चार्जेस यहाँ से पास होते होते यहाँ पर एक्यूमुलेट नहीं हो सकता ना, क्योंकि एक्यूमुलेट जब होने लगेगा, मान लिया केस इन विच accumulation of charges are there, it means should become more positively charged or more maybe more negatively charged. नेगेटिव पूरा भर गया है इसमें. Then electrons will not tend to come here, right? Because it will face repulsion. If there is some negative charge accumulated at certain point, the electrons will be repelled and they will not reach there. उसकी वजह से तो हमारा करंट ही फ्लो करना बंद कर देगा. इसकी वजह से एक्चुअली कभी एक्यूमुलेशन नहीं होता चार्जेस का. इसकी वजह से जितना चार्ज dq1 एंड dq2 आया है, उतना ही चार्ज dq3 एंड dq4 चला जाएगा इस पॉइंट से. दैट इज कॉल्ड किरचॉफ्स एम्पियर्स लॉ। बेसिकली एक पॉइंट पे जितना कोई भी जंक्शन है पूरे सर्किट में, उसमें जितना करंट आ रहा है उतना ही करंट उससे लीव भी करना चाहिए। दैट इज कॉल्ड किरचॉफ्स एम्पियर लॉ। ऑलराइट, अगर ये क्लियर है तो अगर ये क्लियर है तो क्या मैं लिख सकता हूँ यहाँ पर I1 प्लस I2 is equal to I3 plus I4? Of course I can write that, right? Now I have another law which is called Kirchhoff's loop law. First one associated with the currents, the second one, loop law, is associated with actually more potential. Actually, to the fundamental it is potential, but whenever we try to expand it, it also includes currents and resistances as well. But let's consider this a circuit. I'll just tell you how to apply. Maybe I should place a voltage here. Yeah, maybe that would be better. Let's take the example of this one. Abhi, basically loop law tells you that within a loop the total drop in resistance, drop in voltage is going to be zero always. Basically अगर एक लूप है, मान लिया ये, तो इसमें टोटल ड्रॉप जो रेजिस्टेंस का हो, ये वोल्टेज का होगा, अगर मैं पूरा लूप में जाऊं तो वो जीरो होना चाहिए। तो बेसिकली इफ आई स्टार्ट लेट्स से एट एनी पॉइंट, यू कैन स्टार्ट फ्रॉम एनी पॉइंट, लेट्स से ए, इधर करंट जा रहा है, ठीक है, तो मैं करंट के डायरेक्शन में जाऊंगा। तो करंट जाते जाते यहाँ पर हुआ क्या, यहाँ पर आर रेजिस्टेंस था, तो यहाँ पर पोटेंशियल डिफरेंस कितना क्रिएट हुआ होगा और ड्रॉप हुआ होगा। Whatever potential is there, it is dropping at this particular point, right? So potential drop across any resistor could be written as minus IR. All right. So minus IR basically tells you that it is the potential drop, I multiplied by R. And if you go from here to here, nothing is found, nothing is found. Now suddenly you have to reach the point where we started. A point से शुरू किया, A point पे ही end करना पड़ेगा। तो और एक लूप में जाएंगे तभी तो ए पॉइंट पे वापस आएंगे, राइट? तो अभी यहाँ पर मुझे एक बैटरी रखा है जिसमें से स्मॉल टर्मिनल की तरफ मैं हूँ और मुझे बड़ा टर्मिनल की तरफ जाना है। तो स्मॉल टर्मिनल से बड़ा टर्मिनल ज़्यादा पॉजिटिव होता है या नेगेटिव होता है? इंक्रीज होता है वोल्टेज का, राइट? तो आई विल गिव द वी, एंड across any loop it is always going to be zero, summation of all this. So this is the small application of this loop law. I'll apply both of the Kirchhoff's laws in this circuit for as a demonstration. Let's say I1 इधर से जा रहा था और इधर से पास हुआ, अभी एक जंक्शन मिला, जंक्शन से दो अलग अलग पार्ट में करंट जाना है, तो इसको मैं बोल देता हूँ I2, इसको मैं बोल दे रहा हूँ I3. Now as per Kirchhoff's ampere circuital law, I can apply this law across this junction, right? So I1 is equal to I2 plus I3. जितना करंट जा रहा है उतना वापस जाना चाहिए, आ रहा है उतना वापस जाना चाहिए, राइट? सो इफ दैट इज द केस then let's go ahead and apply the loop law. Whatever number of loops are there, you can apply the loop laws across them. Although सारे पे अप्लाई करने की जरूरत नहीं पड़ता है. Let's say the number of loops that can be formed is 3, then the number of loops across which you can apply the equation are 2. because let's consider the bigger loop as the bigger one, then at the end the bigger loop equation will come out to be equal to the summation of first equation and the second equation. So you do not need to apply that much of effort. I'll just apply the Ampere's loop law in this loop and the second loop. First loop, let's call this as V1 and this is V2. Now start from here, A, going here, and this is R1 and R2, R2, R3. First of all, यहाँ पर पोटेंशियल एक ड्रॉप मिला है मुझे, so that will be simply minus I1 R1 because it is a drop, right? Now I have to go to this arm, right? Because I'm talking about this loop. Right by the part से मुझे कोई मतलब नहीं है अभी I2 मुझे मिला और जिसमें रेजिस्टेंस है, तो अगेन I2 डिक्रीज हो रहा है, राइट? ये I2 पास हो रहा है तो पोटेंशियल डिक्रीज होना चाहिए, माइनस I2 R2. अभी यहाँ पर आ गए, लूप खत्म करना है तो वापस इधर जाना होगा, तो प्लस V1 इज इक्वल टू 0. प्लस बिकॉज आई एम इंक्रीजिंग द पोटेंशियल while going from this point to the point where we started. So this is the first equation. I can call it second equation because this is going to be the first equation. The third equation I can write in this fashion. Why? Because there are three variables, I1, I2 and I3. So if there are three variables, I need to have three equations to completely solve each of them. So applying the loop law in the second part, yes, let's start from here, B. यहाँ से मैं गया और यहाँ पर I faced I2, but the current is not flowing in this direction, the current is flowing in this direction. Basically the sign has to reverse, so it will be simply plus I2 R2, not minus I2 R2. अभी यहाँ पर मैं गया तो again it is a very normal thing that current is passing through R2 or R3, yes R3, minus I3 R3, एंड यहाँ पर जाते जाते लास्ट में मैं अगेन स्मॉल पोटेंशियल से बिगर पोटेंशियल जा रहा हूँ, तो प्लस V2 is equal to 0. This is going to be the third equation, and if you solve these three equations you will get the value of I1, I2 and I3, and the rest of the things that is in the question you can easily find. So that was the simple application of loops, Kirchhoff's laws, loop law and junction law. All right, this was the same thing that I talked about. अभी हाँ यहाँ पर आते हैं, क्योंकि हम यहीं पर अभी छोड़ा था हमने कि R1 है and R2 है. If I want to find the net resistance between these two resistors, what I can do is I can compare this system with this as R net, and this has been connected with this EMF. तभी मैं बोलूँगा इसको R resistance, right? Whatever is inside the box, inside this box. तो यहाँ पर हम क्या करते हैं, I है, यहाँ पर भी I फ्लो करेगा, इसमें भी I फ्लो करेगा. क्यों? क्योंकि current can only get distributed at a junction. If only one way of passage is there is this single wire, right? The current cannot get lost or increase. So what will happen is the same current will pass through both of them. Now, just a second. Yes. What is the potential drop across this one? If I write this one, a loop law across this one, it will be simply minus I R1 minus I R2 plus E is equal to 0, right? So what I got from here is E is equal to I R1 plus R2. For this circuit, can I write E is equal to I R net? Of course I can write, right? If I compare this equation with this equation, what do I find? R net is simply equal to R1 plus R2. R1 plus R2 is equal to R net. So basically, whenever I connect resistances or resistors in series, right? It is one past the another. So it is series combination. Then the resistance is going to be get added up. Whereas if I have a connection like this, it is called a parallel connection. They are not just connected one after the another. They are both independent, and this has been connected to E. In this case, both are going to face the same potential. Both are going to face the same potential E and E. And if you want to derive it, then let's call this as current 1 I, this is I1, and this is I2. Then across this voltage, isn't E is equal to going to be I1 R1? Of course. And across the second one, again it is facing the same potential. E is equal to I2 R2. Now if I want to find write E is equal to R1 from here is equal to I1, and E by R2 is equal to I2. What if I add them up? It will be E 1 by R1 plus 1 by R2 is equal to I1 plus I2. What is I1 plus I2 across this one, this junction? It is simply going to be I as per the junction law. So E is equal to, E multiplied by 1 by R1 plus 1 by R2 is equal to I net. And I net could be written in the format of this one. I'm comparing this with the simple circuit in which this is the I and this is the R net. So I is equal to, in this case, I is equal to simply E by R net, right? R net. E gets cancelled out and you're left with 1 by R net is equal to 1 by R1 plus 1 by R2. So those are the two manner in which resistors could be combined together. Now the part we are left with is this one, grouping of cells. Let's call this as I wanted to do it here. Maybe I should erase some part. Yeah. So what this basically is talking about is the grouping of cells. Grouping of cells means we have already talked about grouping of resistors, but grouping of cells means, let's say, no, sorry. This is one resistor and this is one battery and the second battery. If this is the case, then it is simply the case of two batteries connected to each other with alternate phases. It is going to add up to a bigger battery. That's a E1 and E2 and E. So E is equal to E1 plus E2. If they're facing alternate phases, if they're facing same phases, then you'll have to subtract. Now they have complicated it, and we have considered that it also contains resistance, internal resistance. R1, E1, E2, R2. Then what is going to be the case? In that manner, actually, both of them are in series, right? Can I add them up? Of course I can add them up, and E1 and E2 could be added up. So it will be simply the case of this one, where R is equal to R1 plus R2 and E is equal to the same thing. Okay, so series is pretty simple. R is the capital R that is given is the external resistance of the circuit. Now they have also given something that is parallel grouping. In this manner, what is there is, oh, again there is this habit. These are the two cells which are connected in parallel, and this is the power source that I have. They have internal resistance of R1 and R2, E1 and E2. Let's not go into the derivation of this one as it is slightly lengthy. I'll just give you the result of this one that you have to remember. This can be replaced with this one, where E net and this is R net, or a small r itself. That will be simply E net is equal to E2 R1 plus E1 R2 divided by R1 plus R2. This is going to be the net resistance, and of course whatever the net resistance that you have found from here, that will be in series with the external resistance, right? So R net is going to be R plus the resistance resultant of this one, that is the two parallel resistance resistors. So R1 plus R2, R1 into R2 divided by R1 plus R2. It is simply 1 by R is equal to 1 by R1 plus 1 by R2. So I think this has been covered. Potentiometer is a very straightforward application, although it has been removed from your syllabus, so we'll not be discussing it. Then there is only one part left, which is called Wheatstone bridge. It is a simple application in which the circuit looks something like this. The circuit looks like this, and you have, let's say, another maybe another resistor and a galvanometer here. Then if you actually apply the circuital equation, Kirchhoff's circuital equation and the loop law, then you will come to the conclusion. Let's say this is R1 and R2, R3 and R4. If you solve for it, that's the current flowing through this is I5. If I calculate the value of I5 using the circuital laws and make it to equal to 0, then the result gives me actually R1 by R2 is equal to R3 by R4. It basically means that if you have R1 by R2 in a particular ratio as the same one as R3 is to R4, then no current is going to pass through this middle arm of this circuit. So basically, with this having in mind, we can actually find unknown resistors as well, right? So basically, if you have R3 known, if you have something unknown here, you can just put it here, and varying the R3 that you have here, based on that you can find out the unknown resistance. This could be one application of Wheatstone bridge, although there can be many. So if I think that is all for this part of the mind map. We'll meet in the next mind map as well. So thank you.